This lesson has been developed in the framework of SCILED project.
Module 3 Footwear Design Engineering Unit 3 Engineering Footwear for Mechanical and Hydrothermal Comfort.
Lecture 3.2 Calculation of Plantar Pressure Maxima and Distribution.
Introduction. The foot has two important functions: A. To support the weight of the body, and B. To use it as a lever to promote the body in gait and running. Due to its partial construction and many structures, the foot is flexible and can be adapted to uneven surfaces. Examining the footprint that interacts with the floor while standing, it is observed that the heel, area C, the outer edge of the foot, and the front area of the foot, area A, corresponding to the heads of the metatarsals and the third phalanx, are in ground contact. Thus, it is found that during the erection phase, the weight of the body is distributed throughout the foot through the heel, back, and 6 points of contact with the ground, front. However, when walking, when the body is moving forward, the weight falls successively on the outer edge of the foot and on the heads of the metatarsal bones, area A. Examining the footprint that interacts with the floor while standing, it is observed that the heel, the outer edge of the foot, and the parts of the sole that correspond to the heads of the metatarsals and the third phalanges are in contact with the ground. Thus, it is found that when standing phase, the weight of the body is distributed throughout the leg through the heel backwards and 6 points of contact with the ground forward. However, during gait, when the body is brought forward, the weight falls successively on the outer edge of the foot and on the heads of the metatarsal bones.
Gait forces. The forces in the gait cycle and their layout. At the foot, 4 types of forces are exerted while gait. Muscle traction forces. Body weight. Reaction from the ground. Transfer from other parts of the body through joints. The main muscular forces in the foot appear in the Achilles tendon and anterior tibialis.
Measure of gait forces. The maximum force when hitting the heel with the ground during the initial stage of the standing position, typically, is between 100% to 120% of the body weight according to Houston and Williams and Nestor, respectively. With total contact of the plantar area on the ground in flat and mid-stance phase, the load is distributed throughout the plantar area up to the toes. The measure of the reaction force from the ground is reduced from 120% to 80% of the weight according to Williams and Nestor, while Houston reports a reduction in the vertical component to 90%. By removing the body from heel strike to toe off, the center of weight of the human body gradually shifts to the other foot, which enters the first phase of the gait cycle. During the stance phases, the force exerted by the ground is about 120% of the body weight according to Williams and Nestor.
Characteristics of the vertical component. The characteristics of the vertical component, expressed in terms of the weight of the human body where required, show the smallest variations between the foot of the same subject and between different research subjects. The characteristics of the vertical component that have been the subject of studies are the following. Loading rate. Total impact peak. Local minimum and maximum measurements during the gait cycle. These features depend on the speed of movement, the area of the contact area of the plantar fascia and the ground, the anatomy of the foot, the mechanical properties of the foot, the footwear and the impact surface.
Center of pressure. The center of pressure of the reaction of the ground is transferred from the outer rear side of the heel during the initial impact of the heel, to the middle of the toe, during the mid-stance phase, and finally shifts to the big toe, during the toe-off phase. The figure shows a typical plantar right foot outline in which the displacement trajectory of the pressure center for a normal foot, for a foot with pronated and supinated foot, is recorded.
Plantar pressure. Plantar pressures are caused by the ground-to-body reaction forces due to the human weight and other movement-related effects. Footwear intervenes between the plantar surface of the foot and the ground, and its geometry and mechanical properties affect force transfer characteristics. Plantar forces are analyzed into vertical, lateral and longitudinal vectors, of which the most critical ones are the vertical ones. These, if excessive, may cause several negative effects on the human body, like localized discomfort and pain at skin level, loading of the musculature and skeletal system of the human body. High-heeled structures transfer pressures forward. Besides any ill health effects due to distorted gait, There seems to be a correlation between wearing footwear with high heels and a series of medical problems related to the metatarsal bones and the phalanges. In terms of magnitude, the lateral and longitudinal vectors are much smaller than the vertical one, however, they cause excessive lateral and longitudinal friction that may lead to skin blistering. Walking speed affects loading. Higher pace increases the overall load. When running, these loads can be up to 3 times the weight of the human subject. Pain thresholds can be as low as 160 kPa for certain parts of the plantar foot surface. Practical experience shows that any values exceeding 80 kPa in static standing regimes are significant and shall be avoided, through improved sole geometry and selection of materials.
The modern tools of choice for examining plantar pressure issues are based on finite element analysis, which is supported by the existence of detailed and validated digital biomodels of the human foot. The use of digital 3D biomodels is fundamental to the study and analysis of plantar pressures. These models can be used to study stresses and strains of the foot tissues. Constructing biomodels is beyond the scope of the footwear engineer, however. Several researchers have developed biomodels for use in biomechanical studies related to standing and walking.
Finite element analysis, FEA, models for system footwear ground.
Footwear, ground mechanical system. Besides biomodels, it is important to have adequate sole models. Typically, these are created as solid models in 3D CAD systems and then converted to finite element models. What is important to most footwear specialists is the whole footwear, ground mechanical system. The foot sole system is usually loaded by the wearer's weight and the footwear and footrest resistances in the various gait phases. Analysis of this system results in the calculation and visualization of foot strain effects such as maximum plantar pressures. Kalkalaki et al. Have investigated the effect of materials on the layers of the sole on plantar pressures. 3 FEA models are created to simulate the 3 major gait phases during walking, i.e. heel strike, mid-stance and toe-off. By running the corresponding FEA analysis, the applied forces, reaction forces, and the plantar pressure distribution are calculated. One of the most useful outputs of such simulations is the visualization of plantar pressure values and distribution through fringe diagrams.